Perfect. Great. Wow, early. Not the usual control chaos. And so, just a couple things. I'm a little bit sick, not contagious. This is the last annoying raspy throat cough. I got the good stuff. I say it's good stuff because I can drink that and I can still drink wine, so. And you know the antioxidant, whatever. And if you've attended any of my previous presentations, this will be very similar. Just FYI, you can stay for additional reinforcement. And initially it was going to be I thought it was going to be 75 minutes, and it isn't. And so I neglected to update the content. So I got to cut down some stuff, and I'm going to skip some things. However, the slides will be online, and you'll be able to look at them, the things that I skipped. And probably, I guess, while people are still coming in, probably most everybody's here. I guess I should probably ask, how many people are new to deep learning, like 0 to some? Okay, you're in the right place. At the same time, I want to say that I'll possibly, be taking some of you out of your comfort zone. Not because I'm a meanie, but it's part of the learning process, it's, at least for me. And so the good part is that later when you see it again, it'll be easier. You know, that's how it usually works, right? So basically what I want to do is go over concepts, because when you understand the concepts, then when you see the code, it's pretty much the same. So there's something called max pooling, or rectified linear unit, or convolution. If you don't know that, you will by the end of this session. And then when you read the code, it's in Python, or it's in TensorFlow, or Theano, which is going away, or some other language. It's like, oh yeah, okay, ReLU is ReLU, and max pooling is always the same. So you'll be able to apply the theory, or at least understand that, with multiple languages, rather than showing you code, which I made the mistake of doing myself, trying to understand it. But if you look at the APIs, all the options that are there, all the variations and that, I just got nowhere. And then when I started focusing on the concepts, things started happening. So that's sort of the preamble rationale for why I'm doing it this way. So it starts at 2. Should we start now? Yes. Okay, well, welcome everybody. Glad you could make it. I'm Oswald. I will be your tour guide for the next 45 minutes as we learn a few things about deep learning. This is a bit of the kind of the stuff we're going to look at. Not sure if I'll be able to get to the Android part, but probably most of the rest. And so this is just one diagram that I found. I'm not sure if all of it is correct. I don't know really how the data-related stuff on the left is, but just in case you want to see the overall picture, we're going to focus on deep learning. This diagram is a little bit incorrect, actually, because there's something called reinforcement learning that's not there. And reinforcement learning, you've probably heard of with AI systems where they play games against themselves and they get better, like AlphaGo. That's reinforcement learning, which technically is not really deep learning, but it can use deep learning. So modulo that. 2016, it was interesting. There was no deep learning on that chart, even though last year, pretty much all of us had heard of it. And so this year it's there. And so machine learning is actually separate, even though it's a subset of machine learning. And it makes sense because arguably deep learning has been the driving force in the last, 10 years or less in AI. So I think it kind of makes sense. Now, these 5 people started something. It was the summer of 1956 at Dartmouth, and it was the first AI conference. One of them there is John McCarthy. Has anyone heard of him? The creator of Lisp. Oh, imagine that. They used Lisp for decades. Another one is Claude Shannon, who started information theory, and he was called the Da Vinci of the 20th century. And there's Marvin Minsky, one of the giants from MIT. So the 50s were sort of where things kind of started to sort of more or less officially establish themselves. In 1959, there was somebody who used machine learning to play checkers, and it was a modest program. And there was also something called a perceptron, which was the foundation for deep learning. That was actually more from the 40s. So by the end of 1959, 1960, it was sort of established. And this is what we're going to be looking at today. Go through the whirlwind of how the heck does this thing work? Well, just at a high level, we'll come back to it more. You start with stuff on the left, some numbers. You go through these intermediate hidden layers, and then you go to the end. And what's not listed there in those line segments, there are weights there. And they're initialized, and it's a topic unto itself, how to initialize it, because it can make a difference. And so when you get to the end, then you come back. So left to right is forward propagation, and then the other direction is backward arrow propagation, or just backprop for short. And that process of going backward is to update the values of the weights of the line segments in order to improve the neural network. So that's called training the network, or training the model neural network. And so what happens is the input layer, or well, the hidden layers, first of all, it's not voodoo magic. These are just intermediate computational layers. Now the question you might ask is, how many do you pick? That's not an obvious answer. It's called, the intermediate layers are called hyperparameters. And those are the things, they're kind of the knobs and dials that you adjust before you actually do the learning. So they're kind of external. And the number of layers and the number of nodes, neurons, is kind of a variable thing. It's kind of, you do it by practice, intuition, you kind of sort of learn yourself as well. Generally speaking, you favor more layers rather than neurons per layer, because at least in the case of convolutional neural networks, as you go from left to right in those hidden layers, there's a kind of a hierarchical system of representation that occurs. So in the beginning, you get, the first one will, for an image, let's say, would find line segments. Then the next one over will take that and find polygons, shapes. Then the next one starts adding more complexity, and then there's an ear and an arm and a this and a that. So that's why you tend to favor more layers, just in general terms. Now, the other thing is all these numbers in there, all these line segments, they're represented with matrices. That's where the matrix stuff comes in. People call it linear algebra. It's just matrices. The beginning stuff, most of the stuff. And then the stuff on the left, the input, is a vector. So that's why you need to know how to multiply a matrix and a vector. In addition, this is actually a linear system. So as is, that means you could take all of those matrices, multiply them together, one matrix, collapse it down to input and output. You don't want that to happen. It defeats the purpose of having the neural network. So you have to introduce nonlinearity. And that's done with things called activation functions, which we'll look at. And sort of by way of analogy, when I first saw it, my thought was, oh, it's like going to Safeway, and you're in the parking lot. Can you go from one end to the other at the same velocity the whole time? There are those very necessary but slightly annoying speed bumps, right? So you're driving along, you slow down, and then you speed up again. And then it's kind of annoying, so you move over to the side because all four wheels, right? So the passenger, you relieve them a little bit, but if you're the driver, it's still kind of annoying. So up and down, up and down. That's kind of the purpose of these activation functions. The analogy being the nonlinearity, not the thing about slowing it down. Just nonlinearity, so you can't just fly from the beginning through to the end. So those are some of the things that we'll look at. So activation functions, the matrices that are involved, backpropagation, and when you have at least 3 hidden layers, that's called deep learning, believe it or not. And let me see, I'm sort of skipping around a little bit. I'm going to try to interleave things, sort of breadth first approach rather than deep, because there's a lot of kind of parallel topics that need to be kind of introduced. So just to give you a bit of a differentiation about the different, there's similarities and there are differences in AI. So let's look at a little bit at the differences. If you look at traditional AI, and you were to pick one word to describe it, what would it be? I would pick rules. And of course, some decision logic, conditional logic. And from our perspective now, it looks maybe kind of sort of quaint, and maybe some people think it's lame. However, with traditional AI, it was possible to create very powerful expert systems in the 1980s that could match and surpass the ability of humans in medicine, actually. So at the same time, or sort of in parallel, there was, we've got machine learning and deep learning. Those are differentiated. One thing is data, especially with deep learning. Algorithms is another thing. Very powerful, inexpensive computing power. That was a huge one. And the fourth thing is the neural networks, particularly, especially for deep learning. And so skipping over 20th century, we get to the 21st century. 2009 was a year where it was actually called the AI Big Bang. Has anyone heard of that? It was AI meets GPUs. So, we all lived through it. Obviously, we're more interested in other things. No big deal. Then in 2011, somebody came up with a neural network with 6 hidden layers. 6. 60 years, 6 layers. Obviously, things were not progressing very quickly. That's one of the reasons that people said, there's not really much happening here. Is it worth it? It's an academic exercise for academicians who just get NSF grant money to fool around and do whatever. It's useless. Not so. Some of the very, very smart people came into the picture, and actually the stuff that I had in the beginning, that stuff was being done 30 years ago, 1980s. Yann LeCun, L-E-C-U-N, head of AI at Facebook, was using convolutional neural networks and this and that, but how many of us heard of that stuff in the 80s? Those of us who were around. I know people who worked with AI in the 60s and the 70s. The number of times that I heard people say anything about machine learning, deep learning, CNNs, RNNs, 0. So when I saw this stuff a few years ago, I was like, what is this? The machine learning and deep learning, it seemed like this new topic. It's not. Some people say it's actually kind of old stuff. There hasn't been that much really new. Well, there is a lot of innovation, but the fundamental ideas have been there for 30 years. So then what happened? The 2012, Geoffrey Hinton, who's over at Google, he's one of the founders of deep learning. With his team, they won a competition. They had a neural network, 150 hidden layers, starting to move up. Shortly thereafter, Microsoft comes out with a neural network with 1,000 hidden layers. So now we're starting to cook with some gas here. And then in 2015, November, TensorFlow came out, still didn't really affect that many people. And then what happened? AlphaGo defeats the top Go player a decade sooner than expected. The other thing that happened, which you may not know, is that the translation that was being done, or is being done, at Google between Japanese and English in particular, when they switched over to deep learning. But before that, if you could get a 2% improvement in the accuracy, that was like party time. Bring out the champagne, we're going to celebrate, somebody's going to get a bonus and this and that. They switched over to deep learning. It improved overnight 49%. That is an astounding accomplishment. And when I heard about that, that's sort of when I kind of drank the Kool-Aid about this deep learning. So the kind of went through some of this, and so what do they have in common? Before I continue, there's one thing I meant to say that regarding deep learning. You're probably wondering what's up with deep learning and what's the big deal. It's kind of an amazing area. The stuff that it can do is really, really powerful. And it can do wonderful things, except when it can't. And you'll see an example of that shortly. A little foreshadowing here. So we talked about the differences. What do they have in common? They use models. And a model has 2 characteristics pretty much in whatever field that you're looking at. One is how well does it represent the system in question. The other is how accurate are its predictions. So we'll start with a very simple one and then kind of extrapolate from that a little bit. And so now I need to ask, who has worked with linear regression? A few. And for those of you who have not, do you remember from high school math the equation of a line in the plane? Okay, good. And if you haven't, it's y equals m times x plus b. X is the horizontal axis, y is the vertical, m is the slope, b is the intercept on the y-axis. So just a 30-second review. If you take that line and you shift it up or down, that increases b or decreases respectively. If you rotate it one way or the other, you increase m or decrease m. That's it. And then if you flip it the other way around, same idea. Those are lines. You look at that line, it kind of looks like it fits the points there in some way. Visually, it seems like a good fit. So if you take the line, you move it up or down, it's less of a good fit, somehow intuitively, right? And likewise, if you rotate it, you can quantify that. And the way it's done typically is called mean squared error. And what that means is you take each point, the y value, and the y value that it would have if it were on the line. This is our ideal line. Take that quantity, square it, so nothing's negative, add them up, divide by n. That's the thing that you want to minimize. That line represents the minimum of that expression. Does that make sense? So I talked about squares, so it's power 2 polynomial. That's a quadratic. That's a parabola. And there's m is one direction, and then there's b in the other direction, so it looks like that. So we want to find the minimum. So you take the partial derivative, because at that point the tangent slope is 0. So who remembers derivatives? Okay, for those of you who haven't, it's the derivative gives you the slope of the tangent at any point on a curve that's differentiable. And so if it's x squared, the derivative is 2x. If it's x cubed, 3x squared, x to the fourth, you get the pattern. If you have multiple variables, you take the derivative, you have to hold all the variables fixed except for the one that you're looking at, so it's a partial derivative. So you treat the others as a constant. So if it's x squared y, the partial derivative with respect to x is 2x, and then the y is there because it's a constant. If you take the derivative with respect to y, the partial derivative, the x squared is a constant, the derivative of y is 1, you get x squared. That's the basic idea. That's all you need to know. Remember Father Guido Sarducci? You know, the 20-minute, four-year degree in 20 minutes, economics, supply demand. That's it. So that's the approach we're taking here. And cap and gown, all for $80. I loved it. So let's take a look at this, back to where we were. Suppose we're going to use this to estimate and predict housing. So square footage on the horizontal axis, cost in the vertical. Kind of sort of looks like it would fit reasonably, potentially. Crude, but it'll fit. Now, what if we take all of those? Now we're going to get something more accurate because we have 6 different things. Now the equation is not going to be y equals mx plus b. It's going to look like that. Now the w's, see those w's? Those are the weights. Those are the things on that neural network that I showed you. The x's are the values. So they're probably going to show up in your mind, visualize, an Excel spreadsheet. So you'll have x1 to xn, there'll be numbers. You actually go out and you check. And then there'll be a cost. There's a price for that house for all the data. If you have that, which we're assuming in this case, that's called supervised learning. If you don't have the answer, that's unsupervised. So that kind of the reinforcement learning stuff, unsupervised. More complicated. That means more probability statistics, all that fun, tedious stuff. So anyway, the W, so this is where you'd have the W. So that node on the top left, it goes, you're going to get the left edge here, you have x1 to xn, and notice that they all feed into that top node. Then you're going to have the same thing, all these nodes feeding into the next node below, and so forth. That's why you need a matrix. And they can be huge. Correct.
It's not self-like, you don't have nodes connecting to each other in the same layer?
Correct. Correct. There are systems that do that, but in general, with this sort of the model that we're looking at, you can think of it like this, which is what I did when I said, oh, it's a bunch of contiguous bipartite graphs stuck together.
And the second is that it's not firing or whatever, it's not active when
Correct. So that's why it's a limited analogy between the biological system and the actual artificial neural networks. Some attempt to do so, and in fact, that's what Jeffrey Hinton wants to do, because this stuff, he was the guy who came up with this backpropagation. He's like, too old. It's too complicated. The brain, we don't understand. So he's a brilliant contrarian. He's come up with a lot of ideas, counterintuitive, and some of them work, and people, wow. And so maybe he's right. I'm not the one going to tell him he's wrong. Maybe he is right. So again, there's work being done, lots of stuff. It's kind of greenfield, sort of stampede in all different directions. That's why I like it. If you have an addictive personality, you're going to love this stuff. So keeps you honest. And so here's just going to skip over a little bit of this. More stuff. Okay, so we got the activation functions. Now, remember I said the activation function is the thing that's going to make it nonlinear? There are three main ones: sigmoid, tanh, and ReLU, which is rectified linear unit. Sounds complicated, but it's actually the simplest one. Who remembers Euler's constant? Couple? 2.718, blah, blah. Remember when you're talking about taking logarithms, and then people would say, oh, it's the natural log? That's base E, not 10. What's interesting about this number is if you graph y equals e to the x and take the derivative, it's equal to itself. That's unique among non-zero differentiable functions in the plane. It's used in all kinds of things like circuit theory and electricity and complex numbers everywhere. So the sigmoid function is this. So what happens is, see how it's nice, monotonically increasing, smoothed out like that? So that's the thing when you do the input numbers and then the matrix and you get a new set of numbers, you pass those numbers through this function. Not intuitive that this would actually be useful, but it is. It's got some advantages. There are disadvantages. We're going to skip over that part. If you want to think of it a little bit easier, instead of doing this for computations is easier, but if you multiply top and bottom by e to the x, it's actually e to the x on the top and e to the x plus 1 on the bottom. Well, then it's obvious it's a number between 0 and 1. Not so obvious like that. You can look that up on Wikipedia and so forth. Here's another one. Tanh, or as mathematicians like to say, than, like thank you, and another similar, some advantages. So that was the second one that came along. This is ReLU, rectified linear unit. So it goes this, and then 0, it goes up. Very simple. There are variations where you take the exponential one, ELU they call it. Sometimes they drop this thing down a little bit. Sometimes it goes over at 6. All these things that I mentioned are available in all, TensorFlow, Theano, and Keras, et cetera. If it goes over at 6, that's called ReLU 6. That's specific to TensorFlow. Because there's some performance stuff that you can get that was empirically determined. So this is not stuff that's obvious and intuitive when you look at it. It's stuff that people have tried, and they do it until something better comes along, literally. So this is a softmax function. Don't need to really worry about that. That comes in later. There's a little error here. It should be e to the xj over there. And so here's the three functions that I mentioned in Python. Notice here 1 over 1 plus np, that's numpy. exp, exponent, negative np dot wx, right? It's like that formula. Tanh, it's actually literally called tanh. In ReLU, it's the maximum of 0 in the value, see? So you're already understanding the code. And it's going to look like that in other languages as well. It's got to be the same. So what happened, initially it was sigmoid. Let's use that. Then after a while, forget about that. Let's use tanh. Then forget about that. Let's use ReLU. Why? Because somebody came along and did some stuff and said, look, this works better. And so everybody like, okay, well, we'll go this way. That's how it works.
What is an activity function? You have the neural networks and the layers. How does this come into picture?
Remember the analogy with Safeway, driving through the parking lot? Those speed bumps prevent you from driving at that constant speed. So if we didn't have that function to apply at each layer, generally it's the same, it could be different, you could just go all the way through and collapse it down. See, instead of having 10 matrices, multiply them together and you have one matrix.
So this actually, you're applying it to the weight?
Each layer, every time you take the input layer, multiply the matrix, you get another column of numbers. Right. Apply the pass them through the activation function. Yes, sir. And then you have a new set of numbers now, the next matrix, and again and again. It can be massive. That's why the compute power is so important. That's why. And you could have 1,000 columns and 50,000 rows of data. That's a lot of computing. That's why it was useless in the in the early century, because it was so expensive. I saw something about a chip that we have in 2016 or 2017 versus 9 years ago. That one chip on our phone is equivalent to 16,000 chips from 8 years ago. It's kind of mind-boggling. So, yes. Understood. Remember the beginning I said it's a hyperparameter? It's coming up. More activation functions. Let me postpone for a moment. So the cost function that I showed you was a very simple, kind of trivial case in the plane where we're doing the line thing. But you may have other kinds of functions. The one that I just showed you here, with that egg shape there, it's called a convex function, convex surface, actually. So it doesn't indent. So it's very easy to find max minimum. This kind of thing can have maximum, minimum, saddle points. Remember, when you're in 100 dimensions, you can't see where you're at. And trying to figure out which way to go. Typically, the goal is a very simple technique. It's been around for decades, using a greedy algorithm. You always try to maximize the direction you're going, and then at the end, theoretically, you should have therefore achieved the maximum as a result of going through the maximum at each stage. That's not always true. But in general, it works, because data is sort of continuous. It's in the discrete case where you can run into issues. Here's another one. So picking the right cost function, picking the number of layers, picking the number of neurons, and there's something called the learning rate. And all of these kinds of things are not intuitive. So generally, what do? Find something else that already represents something that you're trying to do. Leverage that work. And then kind of through experience. It's like, the guildsmen, the craftsmen, they learn, the journeyman and apprentice, and they learn from the master, sort of. You're kind of like learning as you go, because there's no cookbook. Here, read this book on the weekend, go to a hackathon, you got an MVP. Don't work like that. So this is part of the thing. There's a certain fuzziness about it. There's all this probability statistics, and this and that and the other, and figuring out how all this stuff fits together takes time. Trust me, a lot of time. Progress kind of tapers off for some. So this is some of the stuff that I found online. Look at this. Is that clear? Not to me. You read this and you still don't know. How do you know that something's not clear? When after you've read it, you still don't know any more than before you read it. Then it's not clear. Look at this. This one right here. I'm going to skip this. Hyperparameters. I already kind of mentioned what that is. I'm watching the clock. That's why. Sorry, I'm skipping around. These are some more of the things. Some more hyper. I want to get to one slide here. This is really interesting. Okay, Jeffrey Hinton and Yoshua Bengio. This is what they say. Read that and tell me if it makes sense.
There is no mathematical proof that neural network can work, right?
I'll get to that.
Okay.
I will get to that.
No, but second question. Everything that we are doing is still on, like you say, the basic principle of neural network. What about if we change completely the model? I don't know, instead of neuron, I don't know, put something else.
That's my next talk for next year. So the first one at the bottom, actually, I took part of it out so it would fit. He goes, actually, Benjamin put it at the beginning. It's very simple, colon, and then puts that in there. It's not. For them, yes, but when you're learning, it's a very tedious process. It's an intuition that you get as a result of having looked at different models, different types of data. You get a sense of what, anybody here a DBA? Database? Okay, so they put indexes on things and this and that, and they're like, oh, okay, well, I think for performance, I'll put an index on this and this. It's sort of intuition, experience, all rolled into one. They don't even necessarily know exactly why. That's a bit of that flavor. So how long does it take to acquire that sense? I'm still learning. So the hidden nodes, see how it's almost circular in a way. Like looking up the definition of a word in a dictionary, you end up at the same, and you still don't know, right? Unfortunately, this is the way it is that I've seen so far. CNNs, sorry, Can I just skip back a little bit? I don't want to give you a headache, but I just want to show you something that is important for you to grasp a little bit more. Okay, you remember I said that the data comes in, you do the activation function, the matrices, blah, blah. Let's pretend that at the end there's only one node that goes out. Let's pretend we're looking at the data for the housing, the price of the housing. So we go through, the first row comes in the column, it goes at the end, computes this number. Then we look at the spreadsheet, we've got the value. We compare them. Are those two numbers going to be the same? How can they be? This was initialized with random numbers. So what happens is you look at the value that's on the spreadsheet and the value that's computed, at least calculated, and there's a gap, there's a difference. That's called the error. And then you go, well, each one of those nodes coming in contributed a proportional amount, maybe 50% of the final answer, so it gets 50% of the blame. And with that cost function, I didn't describe it much before, but the business of this, the greedy algorithm, you want to, whenever you're on a surface and you want to go to the bottom, which direction do you go? Well, think of it like when you're skiing. If you want to get to the bottom of the hill as fast as possible, you go down the one that's the steepest, right? That's gradient descent. We have this cost function with all of these different parameters that we can't even see. So we've got these partial derivative in there. And what happens is as you go back, you have partial derivatives along each of those line segments, and you take the product. And while we're here, we also use something called the learning rate. That's like the aileron on the plane wings. You keep going with the same speed, but that adjusts, has an impact on the velocity, sort of. So that product, you then take and update the weight of each of those line segments accordingly. And then you repeat. Now, as you get back toward the beginning, that starts to attenuate. It's like signals, you have repeaters to strengthen it. So the thing is that generally what happens is that the edges that are affected the most are the ones closest to the end, less so at the beginning. In that scenario, there's a vanishing gradient and exploding gradient. That is the rationale for using different activation functions. I'll just leave it at that, just so you know, and then you can read up on it. So when you go forward propagation, back prop, and you do that for every one of the rows in your data set, and you have at least 3 hidden layers, and you do that until the error is either 0 or less than you run out of data, or it's less than a value that's set by you, and you have those at least 3 layers, that's called deep learning. That's it.
You also do that with the node bias value or just the weights?
The weights.
Not the node values.
Correct. Those are intermediate computed values when you go forward. The goal is always to get those numbers adjusted for the weights. Now, here's an important difference. I want to mention that it took a little while to get to this point. What happens in generally, with machine learning, you've got columns where some are more important than others. Number of square feet is more important than whether or not a property is in the corner lot. So you have different weights, if you will, or different priorities. What happens with deep learning, and this is the interesting difference, one that I really like, and I'll tell you why in a minute. Has anyone heard of the central limit theorem? It states that if a data set is large enough, you can approximate it by a Gaussian curve, the bell curve. And when you do that with deep learning, like, oh, okay, it has a mean and it has a standard deviation. So you take the numbers, subtract the mean, divide by the standard deviation. So it has mean 0, standard deviation 1. So when people say, what's your data? Oh, it's N01. That's what that means. Now, we've just leveled the playing field where all of these columns are now N01. But haven't we then lost the information about what's more important, the number of square feet versus number of bathrooms and the other factors? It's lost, right? What do we do?
Any real estate guy knows that location. But most of you look at the data and you see what the data dominates. It's sort of like decision trees.
Sure. We'll have a smackdown, he and I. So the answer to the question is, what do? Nothing. Because given enough data, deep learning extracts the features for us. less work. I love it. Appeals to my infinite laziness. We don't have to do anything. That is one of the key reasons why deep learning uses so much data. There's no such thing as too much data in deep learning. That's why. So I had to give you all the other stuff in order for this to make sense. Now, another little thing, because I have a little bit of a math background, for those of you who have that as well, I like to see things that look totally unrelated, but then they sort of fit together. There's something called Brouwer's fixed point theorem. Has anybody heard of that? Okay, you're going to love this in terms of its total. It states that if you have a compact convex set and a continuous function mapping that compact convex set to itself, there exists a point in that domain such that f of x equals x. What does that mean? Well, if you take 0, 1 and a function mapping 0, 1 to 0, 1, it's going to cross that line. Again, so what? It turns out, I saw that theorem in the proof many years ago. The part that I didn't realize is Brouwer's fixed point theorem is used to prove the central limit theorem, which enables us to normalize the data and let deep learning do the work. See? So we start with something totally bizarre, abstract, and useless. That happens a lot in mathematics, I can swear to that. And then you end up at the other end with something that actually is connected. You can still do it without knowing that, but at least now, in an interview question, you can explain why it works. So just FYI. Or, if there's a lull in a cocktail party, you want to just drop it on them, go right ahead. How to lose friends fast, So that's the whole digression I wanted to go back to. We've got 15 minutes. And so does that answer your question? Somebody asked me in the beginning. Oh, here's another thing. There's something called the UAT, Universal Approximation Theorem. This one I love too. It states that given any continuous function, let's say we're looking at the plane, there is a neural network that can approximate it to arbitrarily close precision. Does that mean much? Well, thing is this. The set of continuous functions contains a set of differentiable functions. It's a really big set. To be precise, the set of continuous functions has uncountably infinite number of functions, and every single one of them has a neural network that it can be approximated by, which tells you the expressive power of neural networks is enormous. That's the thing to keep in mind. So the two. Now, that theorem that I mentioned is an existence theorem. It doesn't say how to get the neural network. It doesn't give you the algorithm and the complexity. Just says it's out there somewhere. And there may be more than one. Yes?
Is it true that this theorem is right for just a single hidden layer?
Like I just mentioned, it doesn't tell you how many layers. It doesn't tell you how many neurons. It just says there is a neural network that exists that you can use to approximate that continuous function arbitrarily close. Kind of amazing, isn't it? They are extremely powerful. So it's not like, neural networks, 200-300 good use cases and the rest is just sort of a fluke. Just as a digression as well, there's an interesting thing I read about last week that there was a couple of people came up with a barcode scanner for blind people. And it costs about $20, and it uses deep learning. And the other device costs $1,300. And so people are buying it and using it. What happened after that? This is the really kind of fascinating part. This neural network learned how to read the dietary information, the ingredients and the percentages. How the heck did it do that? It wasn't trained to do that. It wasn't directed in any fashion. That's the kind of interesting part about neural networks. If it's a good thing. If it's not so good, we'll see that in a minute. So, sorry about the jumping around here. CNNs and RNNs, convolutional neural networks. Those are 60% roughly, probably still today. RNNs, the darling of the RNN world. It's not it's recurrent neural networks. It's not recursive neural networks or a bunch of others that are there. They're called LSTMs. Long short-term memory, which is kind of like a collection of a bunch of tiny little neural networks connected, and they backpropagate and they store all this data. They're massive, and they're a lot more difficult to train, and there's not a nice, intuitive, simple geometric graphical model, unlike convolutional neural networks. Has anyone worked with a convolution? what that means is, here's an example. I don't know if you can see it. The green part, see it's 3 by 3. There's a convolute, that's a matrix. Pretend that that's part of the PNG. We have an image, it's got all of the values between 0 to 255. And so we're going to take a little matrix there, and we're going to just superimpose it and multiply component-wise, and then add. So you see the 1 up there times the 42, that's why it ends up with 42. So this is what happens with convolutional neural networks to do image processing. First is the convolution, then there's ReLU, we talked about that, and then there's something called max pooling. We'll look at that too. The idea is you take some matrix, you don't know what it is, I'm not going to tell you because you won't be able to see it. It's part of the framework that you're using. It's going to come up with some numbers. You can pick 3 by 3, 5 by 5, even 1 by 1 actually. So you specify the dimensions, it's going to have some numbers, then here's your big PNG array, and then as you scan across, you do that convolution, and then you populate another array with the numbers that you get as a result of this product. That's the convolution. And it's a little bit smaller, but you can pad, minor detail. Then what happens, ReLU, you make sure that anything that's negative is replaced by 0. That we saw before. Then, let's see if I've got it here. These are sort of some examples of what effects you can create. These are Photoshop, those programs, they use this stuff. A blur, you see the averaging part? That takes out the spikes, as you move across, so it smooths it, but it also blurs it too, so there's a trade-off. If embossing gives you that kind of rich kind of effect, that's it. Just that little thing right there. And so I couldn't find any really nice diagrams, but these are just some examples. You see, it's all smushed together. It's going to take you a while for this to make more sense, so I would recommend further reading on your own. This is the max pooling. So we did the convolution, then we did the ReLU, then you divide it 2 by 2, take the biggest number, plop it over there. Now you've got a half-sized array. So you've lost information. Yes. Does it matter? No. Why? Think of compression algorithms for images. There's lossless and there's lossy. What is JPEG? Lossy. Same idea. You pick the main part, you get the real essence of it, you make it smaller, and you can forget it because it doesn't even make any difference. That's why it works. So, convolution, ReLU, and max pooling. Remember I said you know what these things mean? I did 40 minutes ago. Now you know what they are. Now you do it again, a second time. Is this starting to sound a little bit weird? It gets weirder. When you're done with this and the back propagation and back and forth, at the end you have this fully connected layer. And let's pretend, let's see if I've got it. Do I have it? No, maybe I don't. I'm going to do, there's a famous one called, let's just fake it. This one here. Let's just pretend that at the other end we're going to do MNIST. Those are the digits from 0 to 9. There's 10 of them. So there's 10 slots over there. It won't be a bird, it'll be a number in an image. So you've done this thing, you've got all of these smaller, remember, you're going to have small arrays that get smaller and smaller, and then you might start with 8 filters, 16, 32, 64, a ton of these little bits and pieces. Now what you do, you stretch them out in one dimension. And then for the top node, the 0 position, you connect that thing to every single one of those things that you just stretched out. Tons of line segments, right? Then you do the same for the second and all the way down to the end. Then, this is my favorite part, you use the softmax activation function. For some reason, I really like that name. And it uses exponents and stuff like you saw before. I'm going to skip it because I want to get to some other stuff. So what happens at the end, you'll get in those 10 slots, 10 numbers, non-negative, that add up to 1. They're probabilities. So the first one's going to be 0.1, and then 0.002, and then 0.7. Oh, so it must be a 3. That's how it works. That's what Yann LeCun was doing in the 80s, 30 years ago. It's old stuff. Some of you probably weren't even born then. Maybe. So that's the funny part is it's not really this new technology stuff. It's old wine in new skins. And again, it's because of the ability to do this tremendous amount of processing for very inexpensively. And it still gets expensive because you're going to do bigger, harder problems. There are problems out there that are Jeffrey Dean said, he's the head of Google Brain, he said you probably want to, when you're working with these neural networks, try to avoid doing training for more than 3 or 4 consecutive days, and you're going to go broke if this stuff, 1,000 layers to do all the training. Remember, it doesn't work perfectly the first time. It may go nowhere. It may become inert, and you got to do some debugging. Good luck with that. So that's the stuff. Now, who's worked with Keras? Okay, ignoring you for the moment. Who has worked with Python? Ignoring you guys as well. For the rest of you, you can all follow along, but I'm addressing it to the people who haven't. Look at what we have here. Keras, activation. Doesn't that look familiar? Then we've got, conv2D, convolution, and, max pooling. Look at that. So we're doing these imports as a shape. 332, that's the image. Don't worry about that. There's a model. We've talked about that. Model.add, convolution, conv2D. Model add activation, conv2D activation, ReLU, max pooling. You already, in 30 seconds, you already know what that model looks like. Kind of, sort of, without ever having touched a line of code. So this is sort of the rationale for the theory and the concepts. Because when you see the code, you're like, yeah, of course, I know what that is. And so, now that I pumped you up with all this fantastic stuff about deep learning, take a look at this. We have a panda, we have a panda. But at the bottom, we have 57.7 confidence. And what's this? 99.3 confidence that it's a gibbon. What's a gibbon? Looks like a panda to me. The thing in the middle is called epsilon, very small. What has happened and what you can do is to make very small adjustments to the values of the pixels, which are numbers between 0 to 55, in an image in such a way that you can produce a new image whose difference is indiscernible to the human eye and yet can consistently defeat any neural network. And I don't mean that the performance, the percentage, remember we said the predictive power, that was the second thing? Not that it's just bad or poor, it's horrible, meaning you can defeat it 100% of the time. Now, this has already been, people have talked about this. We're a bunch of bad dudes here, Al Capone-ish, whatever. We want to be disruptive, or the Raven, right? The Halloween, right? Blow up the city. We get a bunch of our little underlings we give them these little signs that look like paper, whatever, of stop signs. And their neural networks we've modified the images, we've done this thing. This is called adversarial neural networks. So then we take those and we go out at 4 in the morning, or they go out, and they put on all the stop signs that throughout San Francisco. What's going to happen? Chaos. This is a good plot for a movie, by the way.
In the world of physics, we see stuff like that all the time. We call it noise, and we put a low-pass filter that knocks it out. Why does it not work here?
The thing is that you can, if you can identify it as an adversarial image. What if you don't know it? You can't see the difference. Can you see the difference? Well, that's the point. So there's this adversarial relationship. There's the discriminator, that's fake, and then there's the generator, the bad counterfeiters, and we're looking at the money, no, it's fake money. So this is the interesting part. It's a little bit kind of, what's his name? Forgot, Kafkaesque? No, it's the bad guys learning how to make this thing, and then the good guys, we figured out what you do. We're gonna make sure it's too complicated for you. So it's Machiavellian. So what happens is, well, we've got this certain level of ability to detect what the bad guys can do. Let's give them some information on how they can make a better fake product. And then we'll get better at detecting the better fake product. See? Isn't that Machiavellian? Up to a certain point. So it's no longer, it's actually not called adversarial networks, this is, but they're calling it cooperative. Yes, because you are. Hey, here, we'll give you some. That shows a lot of confidence, right? So, we already talked about that, blah, blah, blah. And that was the graffiti art thing. It's the article. You can see it later on. Now, last week I just read, up until then, everybody's focusing on static images to do this adversarial network stuff. Somebody's doing it now with audio. Doesn't that scare you? Wait, no. I didn't say fire the weapon. I said don't fire the weapon. I don't know, another movie plot. There we go. And so you can look at that. There's the deep learning, TensorFlow homepage, playground, where you can I would suggest going there. You can set the number of neural network, the layers and the neurons and this and that, and it's all online. It's really nice. And so we don't have time. I want to get to this other thing. Now, ready for some fun? We've been good, right? We can have fun. Go to this website. It's called deepart.io. It's a convolutional neural network. And what happens is you'll upload 2 images, and then it does this sort of fusion. It's sort of like, what is it, Instagram? Is that the one with the filter? So it's Instagram on steroids to the 12th power. It's got 19 or 17 hidden layers involved. And so you post the 2 things, and it does it. Some of them are really nice. People have come up with some, that's kind of weird. You know, you can look at them. So I am not an artist. However, I took some SVG code that I had, which has JavaScript embedded, generated the images, took the PNGs, those are the things on the right. And then I sort of semi-randomly picked some icon-type people, meaning 2 a.m. Friday night with a beer. And so the first person is Grace Jones, in case you don't know. Some of them are good, some of them are lame, I'll let you decide. The second one is the 2 cats, whatever. Prince, not bad. Clint Eastwood, I've said this a few times to other people, and I'll say it again. Is it just me, or does he look more pissed off in real life than he does in the generated image? And as a bonus, he's coming back to acting. You know, Dirty Harry's grandfather kicks butt or something. I'll go watch. And here, this was Salvador Dali, you know, the melted clock thing. Kind of lame, it didn't work out so well. You know, again, experimenting. Angelina Jolie. The weirdest part is the normal eyes, kind of. And then Arnold, of course, not bad. This one I like. It's got that nice sort of fluid, kind of like with Prince. So obviously you get different effects depending on the image. It's 2:45. Let's wrap up. I just barely, I think, kind of got through the main stuff. This is, if you want to get into it, you can get into a lot of other topics. And some of the books I've written recently, working on, and I did a little free Kotlin course, no big deal. I do Kotlin from the command line instead of from Android Studio, so if you want to see how to do that. And I do training, this kind of stuff. So, that's it. Thanks very much.